dependence, you eventually end up with this product. Looks like that. So I have to come up, with some estimate of the x given y, so it's just the product. So my generative model in this case is that I choose a label according to my prior for label, and then for that given label I choose my variables according to whatever this is. If it's binary variables, Bernoulli, multivariate, then it's multinomial, and if it's real valued, I do Gaussians. This is the Bayes net representation, but you don't care. Never mind. Now, Bayes features conditionally independent given a label. We just have to estimate the parameters, and we directly learn this function via closed form. Why does it work? Same reason I gave before. Just as we get more data, we'll converge to the maximum likelihood estimate, which I've been over. And are we done? Yes. If you specify a generative model for which the assumptions aren't violated, you're done. It's a great formalism. Okay, this is to show that it looks like logistic, so I'm not going to go through that. See, we get to it eventually again. Text classification. So in this particular case, the questions, I just wanted to give you examples for the homework. I probably don't need to go through this given that you guys did a whole homework on it. Yeah, robust smoothing. And those are generative models up to naive Bayes. Questions? Yes?
In naive Bayes, you say P of y given x is P of y times that product, but in the denominator I also have the P of x term.
It has a P of x term, yes.
But is that the probability of that instance of x occurring, or is
that's what it is? So it is the probability of that particular example occurring. So the way to get that is you essentially marginalize out the y. So you consider P of x given y equals 1, P of x, y equals 2, P of x, y equals 3, sum it together.
Yeah.
So you can either do that at a time, or you can just think of it as in the homework. What you did is if you were to do it, you have this 8 value vector, right? And you just take it and divide it by the sum of the 8. And that will give you a legitimate probability. As a classifier, we don't care, because you're dividing all 8 of the values by the same sum, so it's just scaling. So the order remains the same. Did everyone follow that?
Yeah.
Okay. I think the practice exam had a problem that asked about P of x, and that's basically the answer. It's just. Yeah.
Question.
Yeah.
So you mentioned that we do conditional probability because we take there are too many parameters to estimate when we do the joint distribution. What are all the parameters that we're estimating at? It would seem to me that we still have the same number of parameters.
So if we were estimating the joint, and we have a Boolean 8. Eight-dimensional Boolean case, right? So the number of examples in that instance space, if we were to exhaustively, is 2 to the 8, right? If we were to estimate that probability directly, we would have a different probability for every combination. We're making no assumptions about the relationships between the variables.
Okay.
Right?
Yes.
So in that case, we're estimating true the 8 parameters.
But when we select our model, for instance, when we do conditional probability, we still select one path where we factor out we do like a condition.
Right, but that's because the naive Bayes assumption allows us to do that. Right? We're making an assumption that the variables don't have dependence on each other. Right? It could very well be that the probability of feature 1 given the probability of feature 2 could be, there could be an effect there, right? If that's the case, that there's kind of collinearities between features, then naive Bayes is wrong.
Okay.
Are you following it all? Or
yes.
I mean, it's just that. So if we said the joint is every possible outcome in the event space, and there's some probability associated with it. When we say naive Bayes, we're saying there's some probability for every possible outcome, but that probability is a result of there being conditional independence between the variables. May not be true, may be true on whatever.
Okay.
But it's our assumption, and that allows us to learn fewer features, or fewer parameters in our model. Any other questions? Okay. Okay, I'm not going to cover a lot of this, but maybe people have gone through this some, I don't know. But maybe it'll, well, I'm not going to go through this problem, I guess. So this was just an estimate of using, I think this was using naive Bayes to make a specification. So in this case, it was just two variables, and we would have to essentially estimate all possible
Homework
cases.
pass or fail.
And we just saw that alone, you just wouldn't see enough people in the class to estimate age and number of time they spent. It would be like more, the counts would be like 1 and 2. It would just not be interesting. Probably not interesting anyway, but you get the point. And if we had more variables, obviously it would get too big pretty quickly, so we assume conditional independence. This is the number of parameters in the joint. Conditions a little bit better, we just get rid of the y, but not interesting. So this is just too big in general. If we get to 10 to the 9, things like this, it is too big. So what we do is we estimate as a conditional independence chain rule. So I'm just going through naive Bayes again. I probably don't need to, unless somebody stops me with questions. Yeah, so you asked about P of X. P of X in reality has a huge space, but it obeys. I don't know why I wrote that. Kevin don't care. Good news for Kevin. These are like literally my raw notes because I wasn't planning on posting these. So I wouldn't be surprised if there's like swearing and everything, but whatever. Yeah, so you don't care. Nobody cares, not just Kevin. Yeah, so I don't really care. Yeah, so there we don't care, but here we really don't care. So exponential linear, because you would need exponential and the joint. Okay, so we said here homework and your age are actually continuous, so we do Gaussian naive Bayes. Naive Bayes don't care. It's a very apathetic lecture. So you have the same functional form for naive Bayes, you just replace the class conditionals with Gaussians. That's a Gaussian, expected, whatever. You could make assumptions about the variance is common. We did it when we did logistic regression. Gaussian naive Bayes. This was a picture. Terrain rep, yeah, blah, blah, blah. Yeah, everyone knows. The point is that with the equal variance, then these end up being circles of similar mapping, so you don't end up with these curves because one is descending more rapidly. As long as they're both descending at the same rate, then you get linear functions. So this is why we make this class independent variance assumption to get linearity. Does everyone follow that kind of?
So basically, if they descend at similar rates, then...
If they descend at the same rate, then you have a linear boundary. But if one of them was faster, then it would meet at a curve.
Sure.
Oh, and then I mentioned about the error, that we could compute the error here, because you can look at it if it's on this. If I predict one and it's on the wrong side, that's my error. And error cannot be 0. Life is like a box of crappy chocolates. It's good. Okay. Unsupervised clustering. So I talked about mixture distributions, and this was for EM. I'm not going to talk about EM at all right now because it'll burn the rest of the time, and I'll do it on the practice exam. Actually, what I might do is give you a sketch of the practice exam and then give you a sketch of the homework if I have time, and that way it'll be 2 birds. Anyway, mixture Gaussians, just to say one thing, the generative story. is we assume every point is generated by, we choose a Gaussian according to some multinomial or Bernoulli, depending on the number of Gaussians. And then based on that particular Gaussian, I generate the point from that Gaussian. Then I have a maximum likelihood case if you know the Gaussian values. But this is my EM situation that I assumed that I didn't have my labels. So the only thing I'm going to say about EM at this point is the summary. Okay, yeah. So we use the current parameters and my x's to compute some probability of the hidden variable given my observations and my current parameters. And then based on that probability, I use that to put a weight for every point and estimate my parameters if that's the likelihood of the data. I think I say this again later better, but
So you're just filling in holes.
yeah, that's all you're doing. You're essentially saying, take the current model, fill in the hole, and then based on the current value that I fill in there, estimate my parameters again. It's really like
Which function or formula was this?
this is just doing EM in general.
Yeah, okay.
So here, this these would be Gaussian. This would be this probability here. So P of Z is membership, right? So that would be the functional form is membership, and then the update would be recomputing my Gaussians given the current estimate. Yeah, well, this is EM, and I'm not gonna do it now, like I said. Yeah, we'll cover it when I get to it. Okay. And then this is the last. I think you're only responsible for these. The fact that I